So in this part of the video, I'll go over the code that I wrote to develop this entire machine learning model. A couple of things I used, something called Google Colab. It's basically an online, it's similar to Jupyter Notebooks, but it's online like the other Google Docs that you can access. And basically it's a coding platform that you can do. It's mainly designed for Python, and that's where I built my machine learning model on, is in Python. And the reason why I used it is because you can see line by line or group by group of your code to see if it's processing and working without having to write the entire code file and then run it and then have to debug it forever. So it's really helpful for debugging and understanding the entire process that you're doing in your code. And so this right here is what I call the physical behavioral cloning. It's based on the online class that I took, or at least the skeleton structure of this code is based on this class I took through Udemy called the Fully Self-Driving Car course. And I highly recommend that class. And it taught me everything about machine learning models and everything about how they work and how to make them from the ground up. And so it was really helpful in helping me, giving me the ground structure that I needed for this project and making the car autonomous and self-driving. So this file, we'll get to this file in a second. This is basically the physical behavioral cloning file, or this code is used to make my machine learning model. But in order to build a machine learning model, you need to have data for the model to learn from and then make future predictions when you're later using that model. So here in this file, this is just part of my GitHub, which I'll have a link to in the video a little later on. I called this code just drive and record data threading. So basically what this does is my car, in order to have it drive itself properly, what I do is I need to record every frame of the car while it's driving through the Pi camera, as well as that same frame record its matching servo position, which is, the servo position is just telling me the angle that the wheels are at. And basically I make a whole video where I drive the car from my computer on the track to make an entire video, collect all the data, where every single frame is stored in a .csv file, which is similar to a Microsoft Excel file, which basically contains the address of where all those images are saved on my computer, as well as in the next column over in the Excel file, it'll show me the servo position. And then I'll use that, I'll show that later on in the video, but I later use that to train the car. So I'll just quickly go over this one, because this one is a bit more basic for me driving the car from a computer and simultaneously recording the frames as well as the servo position. So here's just a simple startup where I just import the GPIO library, which is the pin in and out library, which allows me to access the pins on my Raspberry Pi, as well as accessing the Pi camera array and just normal Pi camera library. And I'm also going to import sleep from the time library in Python, which allows me to pause and wait at different parts in the code, as well as importing the open computer vision library and something called the threading library, which I'll later get into why I use that, as well as the CSV library, which allowed me to save all this data in a CSV file, as well as the OS, so I can save the file and path location correctly inside my CSV file. So I start out by just defining my pins. So these numbers are just the pin numbers where they're located on my Raspberry Pi. And then I just do the basic setup, setting up the motor pins as outputs, as well as the servo pins to output, and starting out the servo and motor pulse width modulation, which is the PWM, setting them to a range of 100 for the servo and 1000 for the motors, and just starting out the servo at 12.75 PWM, which I found out just through trial and error that is basically straight for my car. So that's the position that I start out to make sure it's starting out driving straight. And then for the motor, it's at 25 PWM, which will basically get the motor started, but it won't actually move the car yet. It's not enough power. So that's just initializing everything. And then as well, I initialize the camera and the resolution to be 320 by 240 pixels with a 10 frames per second frame rate. And then I save that into my PyRGB array, which is just saving that camera object from the PyCamera library. And again, defining that that image size to be 320 by 240. And then I sleep for 1/10 of a second, just so everything can be loaded properly before the code begins. Again, those are just initializing the servos and motors PWMs. And then right here, I started with a blank data_image.csv file. So I just use a Python command to open that file. And then I begin writing into that CSV file. And I just save basically that object to write into the file as writer, which we'll get back to in a second. And image index is one which I'll use later to define all the images that I'm saving into our data file. Now this whole list of different definitions, so these different functions I just made, I actually didn't end up using all of them, but I initially made this in a past earlier code. This is how I drive my car from my computer, where I begin by just printing out we'll get back to that. And we'll get back to this function as well, which is actually recording the data. And then this is driving the car function. So we'll get to that. So basically those are all functions that I've defined. The code starts by doing threading, which again was that library that I said I imported. And the power of that is I call for the threading. Threading basically, it lets me run two processes at the same time simultaneously, which I want in this case because I want to be able to record data into that .csv file that I showed you earlier, as well as drive the car from my computer. So I'm trying to do these two things simultaneously, so that's why I needed to involve threading. So I begin by threading target equals drive, which is just the name of the function, and I'm saying start that function. So we go back up here into drive. It means we're just going to start this thread and continue. So I start with a current angle of 45 degrees, which just makes the car go straight. I call the print function, which again, print is just basically it's a menu telling me which buttons I can press on my computer to drive my car in different directions, to tell what speed it's going at, and to shut it down and stop it. So I call that print, and then I define this global variable as user input, which is basically what I'm typing on my computer. And then I start this while loop where we'll keep going through this. This is while one, so this will always be true. It'll keep looping through this until Z is pressed, which is when it exits and it breaks this while loop. But yeah, so with threading, it calls that drive thing so I can start driving my car, but it doesn't stop there and just keep looping through the while loop. It actually starts it, and then it also then goes on to this line, which I call the function begin recording. So while I'm in this function where I'm basically driving my car from my computer, it'll also start this begin recording function, which is where I use the camera object, which again, as defined above, that is just the camera, the Pi camera of my car, where I call the capture continuous function. So basically it's continuously capturing these frames. So I do 4 frame in camera.capture continuous. So it's capturing each frame at a time from this continuous, basically live streaming video data from my Pi camera, and it's going 1 frame at a time, and for each frame that it captures, it'll enter into this for loop, and then it'll go back to the top, get the next frame, and go in here, and so forth. It'll keep going through that until I call this else, which breaks this for loop. But again, as I defined down here, this user input is a global variable. So this user input is where input, I type in a letter or a certain key on my keyboard and hit enter, and then it'll load that as user input, and it'll figure out where that is in this else if statement. But that user input, that is stored since it's a global variable, and in this begin recording, since they're happening simultaneously or in parallel with each other, it is, every time we capture a frame, it's checking what this user input was. So whatever key I typed on my keyboard. And if it's not Z, and again, as a reminder, Z was the button to click on if I wanted to break this while loop, which is basically I can keep driving my car until I press Z. Then as soon as I press Z, I'll stop driving the car and go into here and just basically close and clean everything up. So that'll stop driving the car if I press Z. So in this begin recording function, for every frame I capture, if I haven't pressed Z yet, we'll keep entering this if statement. What this if statement does is it loads the frame as an array, and I load that into an image. I wait, because I can also, I actually don't even use this, so that I could even just comment out. I don't end up using this, so that's not needed. So I load this frame as an image, and then I basically clear the frame, clear the raw capture, which I'm using right here, which raw capture is up here defined by the pi RGB array. And I need to clear that because that way it's empty, so I can load a new frame into using the raw capture object. So I clear it, and the reason why I can clear that because I already have the frame saved in my image variable. Then I defined the servo's PWM and motor's PWM, and again that writer object that I defined above as an object to just write to the CSV file, and this image index, which I defined up here as 1. So basically I have these main variables right here. Then I call the directory, that's just a variable that I defined as this location in my Pi. So in my Raspberry Pi, this is the location where I want to save all these images to. And then this is where I'm using the OS library with the directory, which I'm just saving this directory into the OS. So I'm saying for the operating system, this is the directory that I care about where I want to put all these images. And then I also name this variable current path, which is again that same location as the directory. And then I define the image name. So the current frame that I just captured from my camera, I want to save that as an image underscore, then the image index. So again, that's 1, starting at 1 since I defined it as 1 right here. It's initially 1 and then .jpeg, so JPG. That way that's the name of the first image I capture. And then I use the OpenCV library ImWrite function where I write this image, which again was that image right here. I write the image I save that image as this name. So this is the name of the image that I just saved. And I'm just saving that in the current directory, which is this right here, since I changed the directory with the chdir function in the operating system library. So basically when I save these images based on this name, they will all go inside this location, inside the image folder, img folder. And then now that I have that image saved, I need to add that to a new line of my .csv file, which is, like I said, similar to the Excel files, where I use the writer object defined up here as a csv.writer. And inside the writer object, I do the current path plus the image name, which is where this is the current image and the image's name. So that's right where I just saved this image. I'm putting that all in a string inside this row. Inside the current row, I put that name in a string inside the first cell of that row, and then the second column I'll save the servo's pulse width modulation, which again is global. So that's like whatever angle the car is at. And I'm also saving the motors if I ever want to use that for later machine learning models, which is how fast the car is going. Since I make them global, that allows me to access these. Even though I don't define these in this function right here, I actually define the servos PWM and motors PWM in these functions, which allow me to drive the car. So basically I write that in a new line of my .csv file using the writer object. And I increase image index by 1, so basically now we're at 2. And we'll keep looping through this, saving every image that I capture, as well as saving the path to that image, the position of the wheels at that image's snapshot, and the speed of those motors. So that's what the begin recording function is doing. It's basically saving all this data while I'm actually driving the car at the same time. That's why I needed threading. Now going back to the drive function, this again is just driving my car where I read in an input, which involves me typing a letter in the keyboard and then hitting enter. And basically if it's a space, then I want to call the stop function, so it'll stop my car. If I typed in G, then it'll go and it'll drive the car at a medium speed. Then if it's H, it'll sprint, it'll go to high speed. S, slow, go to slow speed. Then W is just to make the car go straight. So that's where I call the straighten function. And then D is just to steer the car a hard right. A is to steer the car a hard left, where I'm taking this current angle, which is this variable right here. And to turn right, I'm increasing the angle of the car, and then this turning left is decreasing. And these exact numbers I tweaked with until they were about equal and the car turned and drove well based on those angles. And then this Q and E are for minor adjustments. So Q is to do a slight left and R is to do a slight right, just to help make the car drive more accurately and smoothly. And then M is just basically M for menu. When I type in that, it reprints out my menu of like all the different keys I can type in, and Z again is for exiting. And then if I mess up and don't type any of those, then I'll just print out this statement that it was the wrong input. These functions are very simple that I call. Print is just simply printing out all the options that I have. Stop is just setting the IN1 and IN2 to the motor's H bridge to low, which just stops the car. And then I change the duty cycle of the motor to 25, which is basically 25% of 100% power, which is low enough that the car will stop. Straighten, like I said, the 12.75 is what I found out to be straight for my car. So I just reset the duty cycle of the servos to 12.75. And then slow is just, I do high and low, that just means drive forward. If I reverse those, then the car would drive backwards. And I change it to 45 for the car, 45 PWM, 45% of the duty cycle, which is decent speed. Medium is 55, so a bit faster. High is 80, which is really fast. And then steering the angles for the steering function. So this is when I'm turning right or left. I pass in the angle, which as you saw down here, I'm basically taking this current angle, and for this example of steering left, I decrease that variable, and then I pass that variable, that new adjusted variable of the current angle, into the steer function. So then the steer function passes in the angle, then it does this conversion, which I found through research that this is the best conversion to convert the actual angle of the wheels to a duty cycle value. So I get this DC, the duty cycle value from that conversion, and then I pass it in, then I change the duty cycle of the servo, which is essentially steering the car. And then then I save this global variable, the servos underscore PWM, to be that same number that I put in here to change the car. The reason why I needed to do this is that way when I call this global servos PWM, that number will be updated and the correct number will be saved to the current frame. And that is basically how that's how I record all of the data. So so this is similar thing, I just have a different repository name. But yeah, again, I clone all that data from the repository, from my GitHub, all those images, and I see I have the .csv file and image1 and image2. The reason why there's two folders is GitHub has a limit of 1,000 objects or files that can be inside each repository, and I recorded over 1,000 images inside from my car to train it properly, and so I had to make 2 image repositories to load all those images inside my GitHub. Then I installed the image augmentation library, which you'll see later on how I use that. These are all the libraries I use to build my machine learning model. I use the operating system library, NumPy, matplotlib.pyplot, the matplotlib.image library, as well as the shuffle library from sklearn utilities. And also from sklearn I use train test split, which I'll get to these different files that I use and why I use them, as well as importing the TensorFlow Keras library. And from Keras from the models I get the sequential model, which I'll be used in making my machine learning model, as well as the Atom optimizer from the Keras library. And for the different layers that I'll use inside my machine learning model, I import all the different layer options, which are convolution 2D, max pooling 2D, dropout layers, flatten layers, and dense layers. And from the image augmentation library, which I imported right up here or installed, I import all the augmenters, as well as importing the computer vision, the OpenCV library, the pandas library, and tpath, and the random library. And you'll see why I use all these as I go through the code. So I begin with loading from the data directory. I get the track, my new track, which again is this directory right here. I just call that my data directory. In the columns, since I know how I built my .csv file, I built it so that the first column is going to have the location of my images inside my Raspberry Pi. The second will be the steering angle or duty cycle of the servo. The third column is the duty cycle of my motors. So I just save those as columns, and then using the operating system path.join library or functions, I basically add to this data directory the data image.csv file, and then I name all the columns based on these labels that I created right here. And then using the pandas library, I can read this CSV file. Basically, I can load the different columns and rows from this CSV file, and I save that into my data object. And then I'm just displaying data.head, which is just displaying the first couple rows of my data object, so I can see that I properly loaded the CSV file. This function right here, the path leaf, basically I get this data center, apply path leaf, which is, again, I'm getting the column containing the image, each image location of all the images to train my model. I basically take that path, and then I split the path using the ntpath.split function between the head and the tail, which is basically, this is the head all the way up to image, and then the tail is the image_1.jpg, and then I return the tail. So that way I'm only getting the name of each of these images, and I'm resaving that to the data center variable. And then I reprint that out to see if that is working out well. And you can see that now for each of the rows, I only have the image name instead of the entire path to the image. Now that I do that, I just create an histogram where I plot all of the data to make sure I have no bias data. And I just do a bar plot, which is the data that I'm plotting is just all the steering data from my data that I collected, which is basically just taking this second column in my .csv file by accessing that using the data bracket string steering. And that accesses the second column data. And I'm just putting all that into a bar plot to make sure I have a good distribution, which this is very good. This shows that my 12.75, as explained earlier, that's the basically the car is more likely to choose to go straight in the model, which is important because it's important that the car stays going straight and is not constantly like steering side to side on the road, but that it is more likely to choose straight. And then these two left is showing left and right turns on the car, and they're about equal, which is good. That's showing that there's little to no bias in the car data, which means the model should work out very well. And this function that I built is basically just taking in the data directory, which is either image or image2, as well as the data variable, passing that into this function right here. The reason why I have those two different directories is because, as I said earlier, only the first 1,000 images are in the first IMG folder or repository, and all my other images are in the second folder. So I need to figure out the dividing line where to divide those images. I need to make sure I'm going to the right location for each of those image names inside my repository. This is just going the length of data. So this is basically this is a for loop looping through every single row of my data object. I get my index data, what does that look like? This is showing right here, each data.i location, and then with a value right there, is going to return each of the columns and what their value is inside each of those columns for that current row, which was 1182 shown right there. So basically I take the current row, get all the column data, then in the first column that's containing the image, or what I call center, and then I'm saying these numbers I found out where the dividing line is, where I should divide, as in where the first 1,000 images are. And the reason why it's 1098 is there's some images that I deleted, 98 to be exact, that I deleted inside in the first 1,000 that were mess ups in the data recording. So then I take the first data directory, get that center, which again is this value right here, and I strip it so I get only so I strip it, meaning I'm gonna get only this value right here, and then I add that to my data directory and I join it using the OS library, the first directory, and then I append that to my image path object or variable. In the steering, I'm going to do the same, where I get the first, or this is actually the second column, which contains all the steering data, and I append that to my steering vector. And then this is this is also another range that I wanted to avoid because there was bad data in there. But basically, if it's not less than 1098 and it's not in this range, then we're going to append it to the second data directory, append that image location as well as appending the steering data. And after I go through that whole for loop, I take all those image locations and all that steering data, put it in as a NumPy array, and save it for these two variables, and I return those two variables. So then I get all the image paths as well as all the steerings, and that is shown right here. Or print out the image paths, just showing the path. And again, the reason why I went through all this work, why it's a new path, because the earlier paths in my .csv file, these are for where those images are located in my Raspberry Pi, but I needed to get rid of that head directory and put in the new head directory, so I'm actually loading the actual images from my Google Colab folder that I cloned at the beginning of this code. So that's why I changed that path. And this is just showing all the steering data, and then it's just me making sure that the correct images lined up with the correct image folder and image2 folders. Then I call the train test split function, which takes the image paths and the steerings that I had, and just basically splits them, where 20% of all the data is going to be my testing data or my validation data, and the other 80% is to train. Because with a machine learning model, you first have the majority of your data is used to train your machine learning model, and then you want to validate that machine learning model, which what I have set here is then 20% of the remaining data is used to validate that machine learning model. And then this is a random state just to randomize what that 20% is from. So it's not just like the back end of my data, it's random within all my data. It's random whatever the 20% is. This is just showing that it all worked out, and then I can see that I have 1,284 samples to train my model, so 1,284 images to train my model, and 322 images to validate my model. So I think that's good enough. And then I just plot the bar plot of the two, and again, there's no bias, so this is good. And the car is more likely to choose going straight in both of them, which is good. So I'm satisfied with that. So now I add data augmentation techniques, because basically to not only provide not just more data for my model to learn from, but I need to by changing the data, the model becomes more smart, so to say, that as I distort my images in a large variety of ways, which I'll show, the model can learn more robustly. That way, in the future, when I'm using the model and the car takes a picture on the track, it will, because it's learned from all these twisted pictures as well as normal ones, it's learned from those complicated data objects what to do in those scenarios, then it's a lot more likely to be more accurate when the car is driving itself on the track. So these are just the different functions that I've used. We have the zoom function, which is just going to zoom in on the picture 30%. And this is just showing two pictures side by side, so the original and then zoomed in. Then I have a pan function, which I build, just testing if that works. We see that the original image and then it's panned over down right a little bit. Then randomizing the brightness of the image, we see the original image and it's darker, the same image. Then I randomly flip it. So I have the original image and then it's flipped. And as you see right here, I had to also make sure the steering angle was perfectly reverse around that center medium of 12.75 PWMs for the servos. So that way I don't mess up the model, making sure that the steering is reversed as well as the image. And then this random augment function is basically just taking all those things I just built, so this flipping, this darkening, this panning, this zooming, all those different distortion techniques, and it'll randomly receive an image and a steering angle, and it'll randomly 50% of the time it'll pan on that image, zoom on an image, change the brightness, as well as flip the image, and then it'll return the new distorted image and new steering angle. And this is just me plotting a lot of different things where I pass in just 10 different images into 10 random images into that random augment function to make sure it's all working. So it's looking good that we have this one is flipped, this one is both flipped and darkened, this one looks like it's flipped and darkened as well, this one looks like it's zoomed in a little bit, this one's gotten darker and got panned, this is reversed as well, and you just see that it's happening about 50% of the time. So that's all looking good. So now that my images are all distorted properly, so I have a lot more data and a lot more robust data, I now call the image pre-processed data. And this is the reason why I'm pre-processing each of my images is that way it'll work with my machine learning model, because I'm basing my model off of the Nvidia model, which uses an image size of 200 by 66, as well as Gaussian blur will help get rid of noisy learning from the data. And I'm converting the RGB images to YUV, which is luminescence of chrominance, which is used in image processing techniques for the Nvidia model. And this little range right here of the image, the reason why I'm only grabbing part of the image is that way I don't have random stuff from my image that the model is trying to learn from. Such as in this case, this is showing the result of my original image, and then when I pre-process it, this is the resultant image. So the reason why I cut it off, well, this one you don't It's hard to see as much, but I don't want it to look at this trash can or these chairs or the random objects around the room. I only want it to focus on the track itself. So that's why I have this range of 20 to 240, which I've just tweaked on my own to figure out what were the right numbers so I could mainly only be seeing the track when the car drives. So that's working. Make sure the shape is right. Then this function going for the batch generator is basically used to, I'm going to use this later for my machine learning model where I have a batch size and I find out if the data that I'm working on is training data or if it's not. And so I do go through the batch size. I get a random image from all my image data, which is a random index. If it is training data, then I call the random augment function. I pass in, from the image paths, I pass in the index, sorry, don't pass in the index. Call a random image from there and the same steering angle corresponding to that image. Get a new augmented steering and image. And then if it's not training data, then basically I just read the image and read the steering angle. So I don't need to do any augmentations, because in real time the car is just going to be getting real image and steering data and not augmented data. And then I call the image preprocess function, which again was right here as defined for my model. So I will preprocess the image, and then I'll append that to my batch image variable, and the batch steering variable I append the steering to. And then I pass those back as a yield for as arrays for each of those. This yield is used in Python. It's basically a way to return each of those. So instead of building up all of this data and bogging down the computer and then building a model from it, in real time this batch generator function is actually yielding each of these images based on this batch size. So it'll do a for loop, building this entire batch image and batch steering variables, and it'll yield and pass those back, and then it'll just stop right there. So every time it calls, every time it passes in, it'll just yield these. So that way it generates these images and these adjusted steering angles in real time, making it a lot quicker to process, and so the computer doesn't have to hold all this data and then process it. It's just producing this new data in real time. Then this is testing if it works. I call the batch generator on the train data and the validation data and plot it, and it's looking good. It's looking like it's pre-processing it well, and yeah, everything is looking good. The size is correct, and so forth. Now this is the Nvidia model I use, where I call the sequential, which again was at the top. I'll go up to it. The sequential is at the top, so that's the model that I'm going to be using, the basic layout, and then I'm going to add in these deep neural network layers to the Nvidia model. Well, it's based on the Nvidia model. We're at a convolutional layer with 24 pixel size, the 5x5 convolutional kernel, going by 2x2 pixel steps. And this is the shape of the original image that I pass in. The 3s are for the YUV, which is again the luminance increments. The activation function I'm using is ILU, which is used for, it's not sigmoid, it's a ILU because that's better for images. And then basically, this is based on the Nvidia model, so I do the multiple convolutional layers, 2D layers with 24, 36, 48, 64 pixel sizes. And then later on in the 64, you'll see that the kernel size gets smaller to extract more detailed features using the ILU activation function. And after those convolutional layers, I'll then add the flatten layer to my model to flatten out the data, and then use the add a dense layer to then compress the data, then call dense again to compress it to 50 data results, and use the dense again to compress it to 10 data results using the ILU activation function. So basically there's only 10 is the output of this layer, and 50 is the output of this layer, 100 is the output of this layer. And then finally at the end add the last dense layer, which is 1, which is going to give me the resultant one single output, which is hopefully my steering angle that I want. And then I compile that using the Atom Optimizer with a learning rate of 0.0001, and then I will return that model that I built in here. And that's basically, that's the biggest part of this thing, is that's building the machine learning model. Then I'll call that function and get this model object that I returned right here. Model summary to make sure it built all the layers right. It's looking good. And then I do the model.fit function, which is where I'll call my batch generator, pass in all my training data. And this is saying that there's 300 is the batch size and 1 is true for that means it is training data. And I'm going to have 300 steps per epochs with 15 epochs. I adjusted those numbers to find a good learning rate from there. And my validation data, again, I call it batch generator, but this time it's with the validation data and with a batch size of 150 and 0 meaning that it's not training data, so it's false, with 200 validation steps. The verbose just means I want to print out and see where the model's at in creating it. And shuffle just makes sure that it's random. Every time I get to start a new epoch, I'm getting a randomized, it's randomly picking the data again. So that is all saved to my H variable, which I then plot down here, the lot training data and validation data loss. And this is looking pretty good. So it's not perfect, the validation spikes up there a little bit, but it's good enough for what I want. You don't see it right here because I reran this later, but it got all the way down to about 1% validation loss, which is not bad at all. 1% loss and 1% validation loss, which is very good. Then, since that model was great, I then saved that model as a .h5. I downloaded that from Colab. Then, since in order to run it on my Raspberry Pi, I'm using TensorFlow Lite, so the Raspberry Pi can run a lot smoother and quicker. So basically, I import the TensorFlow Lite library, then I convert the Keras model. So I begin by loading this Keras model from the TF-Lite converter library, and then I'll convert that Keras model to a TF-Lite model. So basically what I did right there is I just took this model right here, loaded it through the TF-Lite converter as a converter object. Then the converter object I call the convert function, which converts it to a TF-Lite model. And then using the Python open function, I then wrote that TF-Lite model as a model.tflite file. And then I downloaded that. And that is basically it. Once that's downloaded, it's downloaded on my computer. Then I uploaded it on my GitHub. Then I cloned it on my Raspberry Pi. And then this is the function that I use to drive my car. I called it drive autonomously. This whole part right here is how I actually use the model. So I begin by importing, loading the camera libraries, loading the NumPy, the time libraries, the computer vision libraries, OS libraries, and the TF-Lite interpreter library, which is basically, it's TensorFlow Lite edition for my Raspberry Pi. Then from that library I call the interpreter function, where I load where the location is of my TF-Lite model. I load that into the interpreter object. I allocate the tensors, then I get the input and output details. Then I check the height and the width to make sure it matches my Nvidia model. And then I do a similar setup as explained earlier, where I define my pins to drive the car, set them as outputs, set the pulse width modulator for the servo and motor, I define my camera and set it up, and then I define this image preprocess. So it's the exact same as used in my Colab function. This image preprocess function right here. It's the exact same function there as here. That way when the car is driving, I load an image, which you'll see right here. I load an image and preprocess it in the same way, and then pass that into my model to predict from there. So the car basically starts by going to this try function, then setting high and low, which is basically setting the car to go forward, and then I set the motor speed to be 40, so it's beginning at the speed of 40, and then I'm capturing data, or I'm capturing frames from the Pi camera in real time. For each frame I load that frame, I show the frame, I process the frame that I just loaded as an image. I pre-process it so it will work for my model. And then I load that pre-processed image as a array, make sure it's an array. And then what I do is basically, this is the whole predictor part right here that you see, is I set the tensor by passing the input data 0 index, which that is going to be the frame, and I'm loading the process image into the input tensor of my interpreter object. Then I call the invoke, which is where it's doing the predicting part, and then I'll get the output from that, which is the output literally is the servo position that I get from that. So it's now from all that just predicted where to steer the car. And then I change the servo duty cycle based on that output data. And then that's it. Then I update this servo's PWM variable. So this is used earlier to print out to make sure it's working. And then that's it. Then I clear the frame, I go to the top and load a new frame. And that is it. That's how the car drives itself. It stays at a constant speed. And then it is just loading these images, pre-processing them, calling my machine learning model and interpreting it, and then getting the result, which is my steering angle and steering the car. And as soon as I press Q or Control C, then it stops driving and clears everything up. And that's how my car drives itself. Sorry for the long recording, but thanks for listening, and comment below if you have any questions. Thank you.